number 11 is to double integrate x plus y whole squared dx over r, where r is bounded by x plus y is equal to 0, x plus y is equal to 2, 3x minus 2y is equal to 0, and 3x minus 2y is equal to 3. Now, as you can see, we have two pairs of parallel lines, x plus y is equal to 0 and x plus y is equal to 2. 3x minus 2y is equal to 0, 3x minus 2y is equal to 3. So, this forms a parallelogram. Now, clearly, such a parallelogram will be in some inclined position, thereby making it slightly difficult to fix the limits of integration. So, one of the advantages of transformations is that we can introduce suitable transformations by which we can make the region look simpler in a new domain. So, what we do is we introduce u is equal to x plus y and v is equal to 3x minus 2y. So, let us calculate the Jacobian dou uv by dou xy. In the first column, we will have dou u by dou x, dou u by dou y. In the second column, we will have dou v by dou x, dou v by dou y. Accordingly, we will have dou u by dou x1, dou u by dou y1, dou v by dou x3 and dou v by dou y minus 2. So, the expansion of this will give us minus 5. This means mod j is equal to 5, dx dy is equal to 1 by j du dv. We will make it mod. So, dx dy is equal to du dv by 5. Now, let us see the effect of this on the problem. You will find that these two equations will reduce to u is equal to 0, u is equal to 2, and these two equations will be reduced to v is equal to 0 and v is equal to 3. So, you can find that u is equal to 0, u is equal to 2, v is equal to 0, v is equal to 3 corresponds to a rectangle in the UV plane. So, you have u is equal to 0, u is equal to 2, v is equal to 0 and v is equal to 3. So, this becomes the region of integration. So, this double integral will now become 0 to 2, 0 to 3, x plus y is already u. So, we will have u squared and dx dy gets transforms to du dv divided by 5. So, these are the limits for u, these are the limits for v. Integration is straightforward. So, let us do this. So, 0 to 2 will keep 1 by 5 outside. First integration with respect to v, then with respect to u. So, you will have u square v from 0 to 3 du. Substitute v is equal to 3 and you will have 3 by 5 integral 0 to 2 u square, in fact u square du. So, this becomes 3 by 5 into u cube by 3 from 0 to 2. So, the output will be 8 by 5. So, if you go through this process, you will find the Jacobian has played a very important part. If this concept of Jacobian was not there, then fixing the limits of integration for this region would mean breaking it up into 3 or 4 smaller regions of Rx or Ry, and integration would become extremely long. So Jacobian plays a very important role in minimizing the effort while evaluating some double integrals. The correct option for this problem is 8 by 5, which is A. Question number 12. In this problem we'll have to find the mass of a lamina on the xy plane. For calculation of mass we require the density. So let's look at the question. The density function is x plus y. The lamina is bounded by a straight line x plus y is equal to 0 and a parabola x is equal to y minus y squared. Computation of the mass. So let's first set up the formula. Mass of a lamina is double integral rho xy dx dy, where there is a density function. Now let's look at the region. The region consists of a straight line and a parabola. Let's first look at the parabola. We can write this as y square minus y is equal to minus x. Y square minus y plus 1 by 4 is equal to minus x plus 1 by 4. So this is y minus half whole square is equal to minus of x minus 1 by 4. So it's a parabola with a horizontal axis, vertex at 1 by 4 comma 1 by 2. So it will be somewhere here. This is a vertex 1 by 4 comma 1 by 2 in the first quadrant. The parabola will have a horizontal axis because of the y square term, and this minus sign indicates from the vertex you must go backwards. So this is the parabola represented by y square, or x is equal to y minus y squared. And to this, x plus y is equal to 0 means y is equal to minus x. So it's a straight line with negative slope. So extend the parabola and you'll have two intersection points. One is origin. This you can find by solving the straight line and the parabola. So if you take a x is equal to minus y and equate it to this one, you will get minus y is equal to y minus y squared. So y squared minus 2y is equal to 0, y is equal to 0, y is equal to 0 or 2. So y is equal to 0 is this, y is equal to 2 is the ordinate of that. So corresponding to that y, x will be minus 2, right? So now this region of integration is spread over y is equal to 0 to 2, x from, this is the lower limit of integration, x is equal to minus y, and this is x is equal to y minus y squared, minus y to y minus y squared. So if you perform double integration of the density within these limits, you should be able to get the mass. So let's do it. 0 to 2, minus y to y minus y squared, x plus y dx dy. So this is a routine integration. However, I'll do the first part, x square by 2 plus xy from minus y to y minus y square dy, right? So 0 to 2, y minus y square whole square by 2 plus y into y minus y square, lower limit, minus y square by 2 becomes plus y squared. So it's a basic question of expanding algebraically, do a little bit of simplification, integrate, and then let's get the output 8 by 15, option B. I will leave this simple exercise of expanding, simplifying and integrating to the student. So option B is a correct answer for this problem. So just remember your formulas. Density is double integral of mass with respect to area. Question number 13. The density function is x plus y. Lamina on the xy plane bounded by x plus y is equal to 0, x is equal to y minus y squared. We have to compute the moment of inertia about the x-axis. So moment of inertia about the x-axis, if we can denote as mx, is double integral y square into density dx dy. So in the absence of y square here, it would become just density dx dy, that would be mass. But density multiplied by y squared and you double integrate produces the moment of inertia about the x-axis. Obviously, you can guess the moment of inertia about the y-axis should be double integral x square into the density. Right. Slightly long problem. The region of integration so integral 0 to 2 integral minus y to y minus y squared into x plus y dx dy. So 0 to 2 with respect to x would give us x square by 2 y squared. Y cube when integrated with respect to x is xy cube minus y to y minus y squared. So let's apply the limits. Y square by 2, I've retained it. X square would be y square minus 2y cube plus y to the power of 4 plus y cube into substitution for x, that would be y to the power of 4 minus y to the power of 5. Lower limit would give us minus y to the power of 4 by 2, then this becomes plus y to the power of 4. So once again another algebraic expansion and then integration, but let me just see how much we can condense this one. 0 to 2, this is y power 4 by 2. Let us see the y power 4 terms. There is another y power 4, another y power 4. So if you count the y power 4s, you will have 1 by 2 coming from here, plus 1, this is another minus 1 by 2. So this y power 4 by 2 minus y power 4 will get cancelled, so leaving 2 y power 4. Right. So let's come to the y power 5 terms. 2 and 2 will get cancelled. Minus y power 5 minus y power 5 is minus 2y power 5. And then of course only y power 6, only one term will remain, that is y power 6 by 2. Right. If you integrate this, you will get 2 y power 5 by 5 minus 2 y power 6 by 6 plus y power 7 by 14, 0 to 2. So this will be 32 into 2, 64 by 5 minus 64 into 2. Of course 1 we can reduce, so it will be 64 by 3 plus 128 by 14, which we can reduce to 64 by 7. Right. So luckily for us, a 64 is coming out as a common factor. So suppose you take that 64 out, you will have 1 by 5 minus 1 by 3 plus 1 by 7. LCM will be 5 into 3 into 7. So 21 here, 35 there and 15 here. So that makes it 64 into, this is minus 20. 21 minus 20 is 1 by 105. So 64 by 105. Option A. Question number 14. There is a problem on the calculation of moment of inertia about the y-axis. Given the density function rho xy is equal to 1 and the region bounded by the straight line x plus y is equal to 0 and a parabola x is equal to y minus y squared, what is the estimate of the moment of inertia about y-axis? So first, the region. This is a straight line passing through the origin with slope -1, and this is the parabola x is equal to y minus y squared. The points of intersection 0, 0, minus 2, 2. This is x is equal to y minus y squared. This is x is equal to minus y. So the moment of inertia about y-axis is double integral x square into the density function. So when you apply the limits, y limits from 0 to 2, x limits from minus y to y minus y squared, x squared into 1 dx dy. This will give us x cubed by 3 from minus y to y minus y squared dy, which is 1/3 0 to 2 y minus y square whole cube. Minus of minus y whole cube is plus y cube. So an expansion is involved here, 0 to 2 y cube minus 3y power 4 plus 3y power 5 minus y power 6 plus y cube dy. Simplification, 2y cube minus 3y power 4 plus 3y power 5 minus y power 6 dy. Straightforward integration, 2y power 4 by 4 minus 3y power 5 by 5 plus 3y power 6 by 6 minus y power 7 by 7. Applying limits, 2 cancels 2 times, 16 by 2 is 8 minus 3 into 32 by 5 plus 64 by 2 is 32 minus 128 by 7. So this is 1/3, 40 minus 96 by 5 minus 128 by 7. Simplify and your answer is 188 by 105, corresponding to option A.